Okay, so now let's continue with our slide set number 12. So Laplace we started last time, and the basics of Laplace actually started from the Laplace eigenfunction. And Laplace eigenfunction very similar to the eigenfunction that we had for Fourier. Just instead of S we have j omega. If you put S equal to j omega, you end up getting Fourier eigenfunctions. So from the eigenfunction property, we actually have already seen the Laplace transform. If you input an eigenfunction, the output is the same eigenfunction multiplied by the eigenvalue. And we have seen that for Laplace transform, the eigenvalue is h of s, which was integral minus infinity to infinity h of t e raised to the power of minus st dt. This is what we have covered earlier once we were covering eigenfunction. Okay, so S in this is any complex number having real part, imaginary part, whatever. Now, why do we study Laplace transform? Laplace transform is basically studied to see or check or analyze the stability of the system. From Laplace transform, we can find out whether our system is stable or unstable. Here it is written that we do analysis of unstable systems. But generally, if you want to find out that if system is stable or unstable, we do Laplace transform and find out about the stability. It is again valid only for continuous time. The equivalent that we have for discrete time will be ZTransform, which will be your last topic of this course, but it will come later. So Laplace transform, first of all, is valid only for continuous time. And why do we study Laplace transform? The main reason is to analyze the stability of the system. That's the main reason for studying Laplace transform. There are other benefits also, but the main factor which the main property or main strength of Laplace is it tells us about stability of the system. There is a relationship between Laplace and Fourier. We're going to talk about that in a few moments. So coming over to the Laplace transform, as I mentioned, we saw this mention of Laplace transform once we were studying continuous time LTI system, and we gave the concept of eigenfunction. If eigenfunction is given as an input, the output is the same eigenfunction multiplied by the eigenvalue, and this is what we actually saw. So if input is x of t, which is e raised to the power of st, then output y of t would be h of s into e raised to the power of st. It's given right here. And h of s itself was integral of h of t multiplied by e raised to the power of minus st over the whole duration minus infinity to infinity. So this was your initial, you can say, exposure to Laplace transform. And this h of s is known as Laplace transform of h of t. And here s is a complex number. Now if instead of having any complex number, we just use purely imaginary value for s, that is, just we take s as j omega, then e raised to the power of j omega t is also an eigenfunction. This was given to us by Laplace. We call it as Laplace eigenfunction. This was given to us by Fourier. We call this as Fourier eigenfunction. And output would be e raised to the power of j omega t, the same thing, into h j omega. So this is just very similar to what we see for Fourier, for Laplace also. The eigenfunctions are very similar to each other. And eigenvalues that we get are also very similar. The eigenvalue, if you see h j omega, this we call as the Laplace transform. And h j omega is called basically Fourier transform. So very similar to each other, and the only difference is we just change s to j omega, or in other words, we just take purely imaginary value for complex number. And we know the formula for Fourier transform minus infinity to infinity h of t e raised to the power of minus j omega t dt. And if you compare these two, it is just s being replaced by j omega. So both of them very similar to each other. So Laplace transform and Fourier transform very similar to each other. And just like Fourier, we can take Laplace transform of any signal. For example, if you take Laplace transform of x of t, it will be of this type: x of t multiplied by e to the power minus st. This product integrated over entire duration minus infinity to infinity. So this is Laplace transform of x of t, and this is how we express it: x of t Laplace transform x of s. Similarly, we can have Laplace transform of anything. Laplace transform of h of t would be your h of s. So we can take Laplace transform of anything. This is just the basics or equation part. The relationship, or how they are linked together, we talked about it earlier also, I believe, but here let's go over it again. So Laplace transform of x of t is linked with Fourier transform. How? If you just replace s with j omega, you will end up getting Fourier transform, which is x j omega. So just replace s with j omega, you will end up getting x j omega, which is Fourier transform of x of t. That's the linkage. That's the, you can say, relationship between Fourier and Laplace. Looking it from the other side, if you just replace s with sigma plus j omega, the real part and imaginary part, and just use the Laplace formula, it will be x of t into e raised to the power of minus st dt, and s is sigma plus j omega. If you just break it up, these two complex exponential, and take e raised to the power of minus sigma t together with x of t, this thing, if you see, this thing is being multiplied by e raised to the power of minus j omega t dt, or in other words, if we call this as x prime t, it will be Fourier transform of x prime t. So we can say that the Laplace transform is Fourier transform of x prime t, which is x of t multiplied by e raised to the power of minus sigma t. Or in other words, if you just multiply your signal with e raised to the power of minus sigma t and take its Fourier transform, that would be actually Laplace transform. So different ways of looking at the relationship, and most commonly this is the relationship which makes, you can say, more sense, and it is easier to remember also. If we just take the purely imaginary part of s, and, or in other words, take sigma equal to 0, then we end up getting the Fourier transform. Okay, so the mathematics part of it, Laplace transform example. So if we take the most common signal that we have in continuous time, e raised to the power of minus at ut, and we want to take the Laplace transform of this, then Laplace transform formula is simply integral minus infinity to infinity x of t e raised to the power of minus st dt. And if you just replace the value of x of t as this, we end up getting the thing right here. So e raised to the power of minus at ut into e raised to the power of minus st dt. And if we have ut inside integral, it will end up just changing the limits. So from 0 to infinity, these two complex exponentials join together, and this will end up giving you the value 1 over s plus a. If you just undo this integral, you will see that it will end up getting this thing. Now this is the expression part. This is just one part of Laplace transform. Laplace transform actually have two parts. One part is just this expression which will give you some function of s. The other part is known as region of convergence. The second part of Laplace is known as region of convergence. So what is this region of convergence? What is the significance? And let's talk about this. And this is basically, if we want to plot this function of s against s, we want to see that for what all values of s does this function converge, and that particular values of s gives us the region of convergence. Let me be more clear on this. Let's go to some blank slide and see. So let's talk about the same region of convergence. Now, whenever we want to plot any function, for example, if you have, let's say, x of t, this is a function of t. So we can just plot this function of t against time, whatever shape and form is there, and this is basically x of t against t. Similarly, we may have another, let's say, function of omega, like xj omega. Once we do transform, it is actually changing the independent variables over. Let's say once we transform from time domain to omega domain, that is xj omega, or taking Fourier transform, we can just plot this thing because function of omega. We can plot it against omega and see what all different types of shape and form we get. So this is what we have been seeing earlier. So if we take Laplace transform, this is basically your Fourier transform, and if we take the Laplace transform of the same thing, you will end up getting a function of s. This is basically the Laplace transform, and this will give you x of s. Now, common sense says that we should be able to plot this x of s against s, but the problem is this s is a complex number, and we cannot express complex number on one axis. Just like we can express time in seconds on one axis, omega in, let's say, radians per second on one axis, we cannot express s on one axis because s has got a real part and imaginary part. What we can do is s is going to have a real part and it has. So I was talking about this function of s, and s being a complex number, it has got a real part and it has got an imaginary part. So if you want to express any point, just like we can express any point on omega on this axis, but to express s, we need a whole plane for this. Any particular point can be expressed on this plane. So this function of s, if you want to plot it, it will be in the third dimension. It will be sort of a 3-dimension, you can say, plot. And in this 3-dimension plot, our point of interest, typically our engineering point of interest, is not what shape that plot has. Our point of interest is that for what region does this function converge. And how do we find that region? All we do is we just mark the location of pole. We just mark the location of pole, and a line going through that pole parallel to j omega axis defines the boundary of region of convergence. Now the region of convergence would be left hand side of pole for anti-causal signals or system, and right hand side of pole for causal. This is simple rule of thumb which helps us in finding out the region of convergence. And how do we express region of convergence? We say that either sigma greater than minus a. For example, if we have a causal system, we can write region of convergence as sigma greater than minus a, or sigma is also referred to as real part of s greater than minus a, or we can just shade this region like this, which is telling us that it is basically the whole region on the right hand side. So this is an important aspect of your Laplace transform. Rather, it is even more important than the expression itself. So coming back to our slide, let's see what we have in store there. Okay, so in this example, we actually saw x of s. We can just take that integral using that formula, putting it in the formula, and we ended up getting 1 over s plus a. And if you see this x of t, this is basically causal. So the pole that we have here, and what is a pole and how do we find a pole? Pole is basically the value of s which makes this whole expression infinity. And how do we find this pole? We put the denominator term equal to 0. We just say s plus a equal to 0. That will give you s equal to minus a. This is your location of pole, and then what we can do is we can just put that pole here on the s plane, and region of convergence, because it is causal, it will be right hand side, and that's what you see right here. So Laplace transform of this is basically x of s, which expression part is 1 over s plus a, and region of convergence is the real part of s greater than minus a. There are three ways in which we can express region of convergence. We can write it as this. We can write it as sigma greater than minus a, or we can just diagrammatically show it like this. So these are basically three different ways in which we can express or show your region of convergence. Now, this is one example. Let's take another example. And in this example, we have this x of t given to us as minus e raised to the power of minus at u of minus t. Now see this. This was causal. Why this is causal? This is because of this u of t, which made it right-sided. So if you just plot it, it will be starting from 1, and this will be your x of t against t plot. So this was e raised to the power of minus at ut. And if we see this, this is minus e raised to the power of minus at u of minus t. And if you plot this, what do you get? Okay, so this side it will be minus e raised to the power of minus at ut, depending on the value of a here. If a is, let's say, a positive value, so you will be having negative value starting from minus 1 and going like this. This will be your plot here, and this is your t. And this is left-sided, so this is basically your anti-causal. Now, if we just basically this inside is the integration part. The interesting thing is x of s, the expression part actually comes out to be equal to 1 over s plus a, exactly the same expression that we saw earlier. But what about the region of convergence? Again, we just plot the pole, which is again located at the same point on the s plane. But because this is now an anti-causal, you can say signal, a function, so region of convergence would be not right hand side, it will be left hand side. And this is how we actually show this. It can be shown this way, it can be shown this, the real part of s less than minus a, or we can just say sigma less than minus a, or we can just diagrammatically show it here. Okay, as I mentioned, for us engineers, region of convergence is even more important than your actual expression. Okay, so this actually shows us about the second example where we saw region of convergence. In third example, we have gone for a sinusoidal signal. X of t is equal to sine omega t ut. Again, this ut is making it sort of a causal system. So if you want to find out the Laplace transform, we can just plug it inside the formula, integral minus infinity to infinity x of t e raised to the power of minus st dt. And this x of t, just for ease of integral, we can just express it in form of exponentials, e raised power of j omega t minus e raised power of minus j omega t over 2j. We can take this 2j part outside, and this ut is just going to change your limits from 0 to infinity, and we end up getting two integrals like this, combining your exponentials. And if we just do the maths, we end up getting two expressions. One is this and the other is this. So 1 over s minus j omega minus 1 over s plus j omega. So these two expressions we end up getting. If you see in this expression, we have a pole. In this expression also we have a pole. So we end up getting two poles right here. And these two poles exist at omega equal to this point and this point, and your region of convergence will be here. It will be on the right hand side because we have this ut right here. So the poles that you get are located as s equal to j omega and s equal to minus j omega. So depending on the value of this omega right here, you will have value here and you will have a value here. This is your j omega axis, this is your sigma axis. So we have two poles, and region of convergence, interestingly, would be the right hand side because it is basically a causal type of a thing. We can combine them together and write it like this or as this. So this is basically your Laplace transform of sine, and region of convergence is the real part of s greater than 0. We can say sigma greater than 0, or we can just plot it like this. So a sinusoid, how does it look like? Three examples in which we came up with the expression part and we came up with the region of convergence also. Okay, now comes the interesting part about the Laplace link with Fourier. Now, first of all, talking about Fourier transform, we know that Fourier transform does not exist for a wide class of signals, especially if you have a divergent sort of a signal, or if your signal is not absolutely integrable. The Fourier transform does not exist. One example of this is e raised to power of at ut for a greater than 0. This would be a diverging sort of a signal like this. Now, because this is diverging, and you will see that the function itself will not be absolutely integrable. So this will give you infinity, because this is basically area under graph, and if it is going all the way diverging, and if you keep going, it will end up giving you infinity. Now, what is to be seen here is that your Fourier does not exist if your, as we say, signal energy is infinite, or if your signal or your function is not absolutely integrable. On the other hand, as far as your Laplace transform is concerned, it exists for every function, every signal. We don't have to even check whether Laplace exists or not. But for Fourier, it will be more appropriate if you first check whether Fourier exists or not. Okay, and Dirichlet actually was a person who gave us the condition for Fourier transform to exist, and we know what the Dirichlet condition was. Coming over to the region of convergence. Region of convergence of Laplace transform is set of values of s for which your Fourier transform of x prime t converges or exists, or in other words, your Laplace transform converges, because this Fourier of this is actually Laplace transform. So a better way of saying it is that region of convergence is set of values of s for which your Laplace transform x of s converges or exists. And how do we actually find the region of convergence? It is, we can display it by drawing a line parallel to j omega axis passing through your pole. as I mentioned, and the region of convergence will be either right hand side or left hand side of this boundary, and this pole and line passing through this pole actually defines the boundary. And we saw in example 1 and example 2 respectively the region of convergence. In example 1 it was this region, in example 2 it was this region, and we saw that in example 1 we had sort of a causal thing, and here we had an anti-causal thing. So the shaded region denotes the region of convergence for Laplace transform, and they are important for us. Okay. Now comes the fourth example, where instead of one we have two complex exponentials which are summed together or subtracted from each other. And if you see, both of them are of the type sum constant into e raised to the power of minus at ut. And we know that e raised to the power of minus at ut has got Laplace transform, which is 1 over s plus a, and its region of convergence is basically real part of s greater than minus a. So this we already know. And if you see this, we have two of it, so we can just take them separately and we can directly write, if this is e raised to the power of minus at ut is 2, so the same constant 3 into 1 over s plus 2, and here e raised to the power of minus at ut with a1, so this is basically this. You can do the math, you can do the integration part as shown here and still reach the same thing. And once we have this, now the interesting part is that this has a pole, this has a pole, and if you just see your poles, one lie at s equal to minus 2, the other lie at s equal to minus 1. Now each of these poles will contribute its region of convergence. There will be an associated region of convergence with this. Now both of these poles are coming from causal signal or causal functions. So this minus 2 also will have region of convergence right hand side, minus 1 also will have region of convergence right hand side. The overall region of convergence will be where both the region of convergence actually overlap or converge, and that will be this particular region right here, the region on the right hand side of minus 1. So it will be real part of s greater than minus 1. They will say that either we can say sigma greater than minus 1 or real part of s greater than minus 1. One the same thing. Or we can diagrammatically draw it like that. So we can just combine them and write it like this, and region of convergence is actually written right here. So in this example, what we saw was that if we have more than one expression contributing different poles and contributing different region of convergence, the overall region of convergence would be the overlapping region, where both region of convergence overlap. And just to give you a simple rule right here is that if you have both the poles coming from causal signal or systems, then region of convergence will be right hand side of rightmost pole. Similarly, if you have, let's say, opposite of it, both the poles coming from anti-causal, then it will be left hand side of the leftmost pole. But you don't even have to remember this. The basic thing that you need to remember is that the cumulative and overall region of convergence is where all region of convergence overlap. So this actually finishes your slide set number 12, where what we saw was the link between Fourier transform and Laplace transform, the expression for Laplace transform, simply this, and this is basically the linkage or relationship between both. We talked about region of convergence. What is region of convergence? How do we find region of convergence? And we saw a few examples for taking Laplace transform. This was slide set number 12. Again, if we continue and see further, you will see that we have not talked about the inverse Laplace transform, and that is what we are going to see in the next slide. That how do we find the inverse? We found an expression for Laplace transform, but how do we compute inverse Laplace transform? That is what we are going to see in the next slide set. Okay. So inverse, how do we take inverse? First of all, just sort of a reminder that what we covered here was Laplace transform. This is expression for Laplace transform. This is how we express it. And Laplace transform, for examples that we did, if you have this e raised to power of minus at ut, Laplace transform is 1 over s plus a. And because this is having ut right here, region of convergence will be right hand side of your pole or real part of s greater than minus a. So using that, we covered an example where we have two of these available to us, and the Laplace transform expression was this, and region of convergence was where both region of convergence for this pole and for this pole actually overlap. So two examples we saw. Now, talking about Laplace transform, once you get the expression of Laplace transform, it will be some function of s. As you see right here also, we have some function of s. So you will have some numerator term, you will have some denominator term. And the way we actually find out pole is we actually put the denominator equal to 0. And the value of s, the roots that we get for the denominator, we call those as poles. So we can have numerator and denominator expressions which can be expressed as polynomials, which can be expressed as factor terms also. So you will see that we can actually mark the roots of numerator term and mark the root of denominator term. The roots that we get from denominator are known as zeros, and roots that we get from numerator are known as poles. So what are poles? Poles are those value of s which make the whole expression 0. What are zeros? Zeros are those value of s which make the whole expression as infinity. How do we find 0? Put the denominator term equal to 0 and find out values of s, or in other words, find out roots of s. And how do we find poles? Put the numerator equal to 0, or in other words, find roots for the numerator, and that will give you the values of poles. So poles are those values which actually make the whole expression 0. Sorry, I have just written it the other way around. Sorry, let me correct it. So denominator contribute poles and numerator contribute 0. So I just wrote it the other way around. It is the other way around. So how can we actually mark this zeros and poles on this plot? What you can do is we can draw that S-plane, and on the S-plane, as I've already shown, the poles are marked with a cross sign, just like you see right here, and the zeros are actually marked with the, let me correct it so that does not create any confusion here, and the zeros are marked with a circle sign. So zeros and poles. The poles are basically, these are poles, and this is basically 0. So on the S-plane, the poles can be marked and the zeros can be marked whatever the value of S is. So this is how we mark the 0, this is how we mark the pole. Okay, so these poles and zeros are very important, and as we have seen that poles actually define the region of convergence. The 0, on the other hand, does not define or does not affect your region of convergence. Okay, so as I mentioned, we can just factorize the numerator and find out the zeros. We can factorize and find the location of poles. And the diagram where we have marked, let's say, the location of zeros and the location of poles on the S-plane, this is known as the pole zero plot. So just if you take an example of poles and zeros and plotting and finding the Laplace transform, let's say we are given this x of t. Now these two are known to us. These are of the type e raised to power of minus at ut. This is delta t. So how do you find Laplace of delta t? We can just take Laplace of delta t will be integral delta t raised to power minus st dt. And because we have delta here, we can directly write the answer as 1, because delta will be 1 only at t equal to 0. At t equal to 0, this is also 1. So we can directly write down this. Laplace of delta t is 1. And Laplace of e raised to power of minus at ut, 1 over s plus a. Again here 1 over s minus 2. Notice that we have plus 2 here, should be minus 2. So just using this formula that we already know. 1 over s plus a. Okay, so again both these poles coming from causal. Both these poles coming from causal, so region of convergence would be right hand side. So we can just mark the poles at one at this pole coming at s equal to minus 1, this pole coming at s equal to 2. Both are causal, right hand side of the rightmost thing, region of convergence right here. Now if we just combine this and write it as a polynomial, we can see that the zeros lie right here. We have two zeros, both lying at s equal to 1. So this is also a pole zero plot and also gives us the region of convergence. So pole zero plot, very straightforward. We just find out the value of s which make the function infinity, or in other words put denominator equal to 0 and find the roots of denominator. And the zeros, we just find out the value of s which make the whole expression 0, or in other words put numerator equal to 0 and find the roots of the numerator. The region of convergence properties, we have already seen it. First of all, it actually consists of stripes parallel to j omega axis. So region of convergence that you get is actually going to be parallel to your j omega axis, either this way or this way, but the whole region parallel to the boundary parallel to the j omega axis. Second property, region of convergence cannot contain any pole. That is again coming from the very definition of region of convergence. The region of convergence is that region where all the points of S has got a finite value function S. Pole on the other hand is that value of S which makes the function infinity. So that pole cannot form part of region of convergence. Rather, pole define the boundary, or it is outside the boundary. It cannot be inside region of convergence, because x of s becomes infinite at the pole. Third property, if you have x of t which is of finite duration and absolutely integrable, then region of convergence is entire s-plane. What it is saying right here is that if you find an expression, function of s, which has no denominator term, let's say s plus 1, nothing in the denominator, then you don't have any pole. And if you don't have any pole, region of convergence is the entire plane. And that typically happens if we end up getting x of t which is of finite duration. If your x of t starts and ends at a particular location and the area under graph is also a finite value, then you will notice that once you take your Laplace transform, it will have no pole. It will have 0 pole, and if you have no pole, your region of convergence will be entire S-plane. So there are other properties also, two properties I mentioned. One property was basically for a causal system and signal, the region of convergence is right hand side of your pole, and for anti-causal it is left hand side of your pole. So If you have multiple poles coming in, then the region of convergence is basically the region which is overlapping. So we see that what all region of convergence is contributed by each pole, and the overall region of convergence is where all region of convergence actually overlap. So this slide set actually was for inverse Laplace transform. So how do we take inverse Laplace transform? The way forward, but again I don't want to start it here. I just want to finish it on this point because I want to start that other point at the next lecture. So I hope everybody is clear on the assignment part. We have assignment number 3, which will be the questions at the end of slide set number 10 and 11. And the due date for that, I will just mention it in the chat part also. The due date is 24th of January, which is going to be Sunday. So any questions on this Laplace transform that we have covered so far?